Welcome back to CSE 369. So in this lecture I want to tell you about sequential circuits and flip-flops. But before we get there, I just want to do kind of two warm-up exercises. So the first one is about K-maps. So we've introduced K-maps in the last few lectures, and I just want you to solve the K-map you see here. So before watching me do it, just stop the video, quickly solve it, and then compare with my solution. So here goes. What I see here is that there are two circles. So the first one is actually a little bit tricky. It's around these edges here. Right, so you have to remember that K-maps sort of wrap around the edges, that there's adjacency between the very left and the very right column and the bottom and the top column. So the largest circle that covers these two ones actually is the circle that covers all of these edges. So this particular circle is not D and not B. And then you need to do one other circle to cover that one here at the bottom. And the biggest circle you can draw that covers this one is essentially the whole bottom row, which in this case is C and not D. Right, and again, what you have to remember here, what I used here is the fact that when you have these x's, these don't cares in your K-map, you can essentially choose them to be either zeros or one, depending on need. And in these, the x's within these circles I've chosen to be ones because it makes it possible to kind of make these circles bigger and hence get a more compact expression of my logic function. Good. Second quick review problem. We've also talked about AND, NAND, and NOR logic some time ago, and we've essentially, talked about how we can convert between the different representations. So here, as a brief exercise, let's do convert this circuit diagram, which is given in terms of ANDs and ORs and NOTs, to NAND logic form. So, okay, again, do it yourself, then check that you're right. Okay. So what I'm going to do here is to get from this AND gate to a NAND gate, obviously I'm just going to insert two sequential inverters in each of these cases. But then I'm actually going to do, so now I have to do something about these OR gates, and what I want to do is is the following. So I'm going to essentially take these NOTs and I'm going to move them right up here to the OR gate. And of course, if you remember De Morgan's law, then not A or not B, so basically an OR gate where the two inputs are inverted, is actually the same as not A and B, where the output is inverted of the AND gate. And so this here actually is an NAND gate, right? And then, of course, I forgot to do this one here, so here there's not much to do other than just inverting these, doubly inverting this output. Okay, so with that, you've essentially converted this to a NAND gate representation, and you could do the same thing for NOR representation, just as an exercise. But the main point is that just a reminder of this, De Morgan's law, and how to use it in this circuit diagram. Good. So now I just want to come to the meat of this lecture, which is combinational versus sequential logic. Good. So previously, as shown at the bottom of the page, we've talked about combinational logic. In a combinational logic circuit, you have input, there's some computation that happens on these inputs, and then there's an output. Like a very simple example that I think we've seen in the first lecture is this sort of controllers for a seatbelt light, where, for example, the seatbelt light should be on if the driver belt is not in, or the passenger belt is not in and the passenger is present. Okay? There's no feedback between the light, or no electronic feedback between the light and the passenger. Hopefully there's some sort of feedback through the person who will adjust, who will put in their belt. Okay. But in a different setting, in sequential circuits, you actually do have feedback between the outputs and the inputs. And a nice example is, for example, the traffic light controller, where in a typical traffic light you go from green to orange to red and back to green. And what that means is that essentially the light needs to know something about the state it is currently in. So it knows that I'm currently green, so next I'm going to be orange. And that information about the current state somehow gets fed into the controller to determine what happens next, right? That's feedback. And of course that system could also have external inputs. For example, if there's a sensor that detects whether a car is present or not, that influences when the light switches, that can be added to this sequential circuit. And so kind of the essence of a sequential circuit is that you have a combinational network that does some logic computation on the inputs, but there's also this element of taking outputs or information about the current outputs and feeding it back into the system. A major potential issue with having feedback is that glitches or errors can be dramatically amplified. Right? We've seen in this previous example that in this autopilot controller, there can be a situation here where the autopilot is not engaged, so the pilot is not in charge, so essentially nobody's flying this plane. And the reason why this glitch occurred, if you remember, was that there's sort of different path lengths. There's a signal here, pilot in charge, that can be true or false, that propagates to this output through two different paths through the same circuit. And one path here is longer than the other. This was 3 nanoseconds or 3 gate delays. This was 2 nanoseconds. And so somehow at some intermediate time of the computation, there's a little error that occurs. And in practice, if this is just a combinational circuit, this error doesn't really matter because it's just during 1 nanosecond where there's nobody in charge. But if you take this output signal at this point and you feed it back into the system, it's of course possible that you kind of amplify the error. And you do this again and again, and you might generate a very dramatic cascade of issues, right? So there needs to be something in a feedback system that allows you to deal with these kind of temporary glitches. And so in practice, to build safe sequential circuits, we're essentially going to use clocked elements on the feedback. So these clocks are used to synchronize operations, and they allow us to hide glitches and hazards. And we'll see here in this example how that works. Okay. So the first thing I want to point out is this is a circuit diagram now showing a clock going up and down, and I'm going to focus just on the positive edges here. So this is the positive edge of the clock. Edge. And I also want to point out that these vertical lines here now are not gate delays anymore, individual gate delays, but some sort of longer time unit. Okay. Now the idea of the clock is the following. So I'm only going to look at my outputs and feed them back into the circuit at the edge of the clock. So here, as I start my computation, I let the combinational circuit essentially do its job, and it computes. And it may be temporarily incorrect in this computation time, but I don't care, because I'll just wait until I've reached sort of the correct output, the computation is finished, and only at that point, after we've reached the valid value, am I going to take the value on the outputs and feed it back into the system. Okay? And so essentially the clock acts sort of as a filter where only at edges of the clock am I going to look at the values I have on the outputs. And that, of course, takes into account this issue of dealing with glitches that are temporary. Okay, but there's a second requirement actually that we need to have to build a sequential circuit, which is that we also need some way of holding state, right? So what I'm saying here is that during this whole time when I'm computing what the next output's going to be, I also have to feed in, I have to keep feeding in the value of the output from the previous cycle, right? So I have to have some way in which I can hold the value. Once I've reached the correct value, I'm just holding it there. I do my combinational logic on these output values, or now input values, and then I update. And so the question is, what is the element that allows me to sort of hold the value for as long as I need it? And the answer to that question is essentially that we're going to use D flip-flops. Okay, so before I'm going to walk you through this Verilog code for the flip-flop, let me very briefly explain the basic concepts here. So the basic idea is essentially, if you want to hold a value, the simplest circuit you could conceivably build is something like this. You have an inverter, you take the output of the inverter, you feed it into another inverter, and you close the circle. And so if this value is 0, then this value is 1. If this value is 1, this value is 0, and this value will be held forever in this system. Okay, so that's a memory element. Of course, it's not really interesting because you can't really talk to it. But you could imagine doing something slightly more sophisticated where you have two NAND gates that take external inputs and you connect them. Something like this. Okay, so now you can actually change the values that are held in these internal wires by changing the values on the inputs. And this is not, I should say, a flip-flop, but it's kind of the basic idea behind a flip-flop. You're essentially creating little feedback loops between inverters, and that serves as a state holding element. We're not going to really go into how you design these systems here, but we're just going to kind of describe here the basic properties of a flip-flop, right? So this is Verilog code, and you'll use this code or similar code in your labs. So the module here is called basic D flip-flop. It has variables Q, D, and clock. So Q is an output, D and clock are inputs, and you're also going to define Q as a register. So this essentially says that Q, the output value on the flip-flop, is state holding. And just an additional comment is that this here is the circuit diagram for a flip-flop. So again, you have the clock input, the data input, and Q is the output. Moreover, we're saying that always at positive edge of the clock, we're going to switch, we're going to take the value of the data input and we're going to write it into Q. Okay? So this is important. So this is essentially like an equal sign, but within an always block, you always have to use this particular notation. And I'll give you an example later as to why that matters, but for now, just remember that whenever you're writing in an always block, always at positive edge clock, you always want to use this particular symbol and not the equal sign. Okay? Good. So let's quickly think about what this system actually does, right? So I said here they have I said that basically always at the positive edge of the clock, I'm going to take the value of Q from the current and replace it with the value of the data. But what exactly do I mean by this? Okay, so here, let's first identify the positive edges of the clock. So that's all the ones I have. And then I'm going to say that I want to know what Q is. Okay, so to get the value of Q at this positive edge, I have to look at what D was right before. So I'm going to say, oh, D here is 1, so this will go up to 1. That's from here. Then I'm just going to hold until I reach the next edge of the clock. Now again I look up here and I say, D right before the clock is 1, so that's the value before the clock edge, so that's the value I'm going to copy over here. And then I hold. Again, now I'm looking up here, so the value now is 0, so I have to go down and hold. Here the value is still 0, so I stay down until the next clock edge. And importantly, so here you can see that there's sort of a glitch in this data. And this glitch gets filtered out because it doesn't coincide with an edge of the clock. Okay. Now at this edge here, I'm still staying low because that's the value I get up here. And then finally here, I go back up because the data input changed. Okay, so this is a very basic, very simple, straightforward concept, but that's essentially what a flip-flop does. Okay, so most flip-flops in practice, or very often, we actually also want sort of another feature, which in this case is a synchronous reset. So we want to have the ability to reset the value of our storage element to 0. If something goes wrong, it's convenient to kind of be able to do that. So we're going to update the definition here. So module D flip-flop now has an output Q, an input D and clock, but an additional input that's called reset. Again, Q is a register. It's state holding. It will change in response at edges of the clock. And then I'm saying always at the positive edge of the clock. If reset is true, I'm going to set Q to 0. Else, I'm just going to set Q to D. So if reset is not true, I'm just acting as a standard flip-flop, so I'm just following my input. But if reset is true, I'm going to set it to 0. The reason this is a synchronous reset is because reset is only executed at the edge of the clock. Great. So obviously the next thing that you'll do in reality is when you're building something, you always run a test bench, as you have probably already done in the lab several times. And so now what this code is essentially just a test bench for your flip-flop. So this is module stimulus. It's a set of parameters in here. So there's registers, clock, reset, and D. There's a wire, which is Q. We introduced this parameter clock delay, which is set to 100. So we'll see in a second what that is. And then we want to test our unit under test is this D flip-flop, where we're assigning the inputs as we've seen before. So we're basically saying assign this wire Q to the variable Q that was previously used in defining the flip-flop. Okay, then we're saying that we're initializing the clock at 0, and we say that always at the clock delay of over 1/2, so clock delay was 100, so every 50 time units, set the clock to not clock. So invert the clock every 50 time units, toggle clock every 50 time units. And then we run the actual test bench. So we say initial, begin. First we're setting data to 0, reset to 1. Let me just quickly write that down. So we're going to make a little table here of what we're actually expecting. So we have time, clock, data, reset, and output Q. The time starts at 0, 50, 100, 150, 300, right? And we said at the beginning the clock was initialized to 0, and it switches every 50 time units. It goes up, down, up, down, up, down. Okay. Then we're going through here, we're saying data at the very beginning is set to 0, reset is 1. And so this is after 50 time units, this is the positive edge of the clock. So at pos clock, what's the next thing that I'm going to do? Well, I'm going to set the reset to 0. And I'm not doing anything to the data at this point, so it's just what that is. So then at 100, this is a negative edge, so nothing's going to happen here. At the next positive edge, I'm setting data to 1, not doing anything to the reset, so this is, nothing happens here. And then finally, here at this positive edge, again, I'm not doing anything, so now I'm reading this row here, and this is just 1 and 0, and then this is where the simulation stops. Okay. So what about Q? That's the only one that's sort of, not immediately specified by the code given here. So Q, it starts out at X. I mean, I don't know what the output is because I only know what the current values are for D and R. Then I can look here and I say, well, reset was set to 1. So by definition of my flip-flop, at the next clock edge, I'm going to set Q to 0. And this is going to be carried over for the whole clock period. Then I can look here and I say, well, reset is now 0, but data, so I'm not resetting, but data is also 0, so I'm just copying the value of the data over here, and I hold that value. At this point, data is now 1 from up here, and so my output will follow the data and switch to 1. Okay, so that's essentially what this particular code is going to do. So it's just going to sort of run through different combinations of the reset and data input values and see that the flip-flop behaves in the way that a flip-flop should behave.